Okay, so good afternoon, everybody. Yeah, I'm recording now. Okay, so what I explained last time, okay, or even the lecture before, was decoder and multiplexer. You should understand, number one, how they work, okay? How they work, how they are different, what is the functionality of each one of them. This is number one. Number two, you should also know the design. And it's not difficult. As I said last time, you just use one end. For each input, you just use one end. So now I'm going to make a very quick review so that before I start the lecture. So I told you we have decoder. Okay. The decoder or any decoder should have, if it has, for example, in inputs, the output here should be 2 to the power of n. Okay, this is how it is. So for example, if you have two inputs, A and B, for example, so in this case, I have 4 outputs here. Okay. So, and we have here, I call this one output 0, output 1, output 2, output 3. Okay. The idea is that if AB, okay, is equal to this, these are all possible cases. Okay. So if it is 0, 0, though this is actually number 0 in decimal, it's number 0 in decimal. So the output, I'm going to call it, for example, I0 here. The output 0 should be 1. And other outputs here, output, okay, I'm going to call whatever D. So anyway, I don't want to use I because I may mean input, okay? So anyway, so D1, D2, D3, okay? So if the input is 0, so output number 0, D0 is 1, and the other ones are zeros. Very simple. If the input is 1, so output 1 is 1, and the other ones are zeros. If the input is 2, output 2 is 1, other ones are zeros. If the input is 3, so output 3 is 1, the other ones are zeros. Very simple. Okay, that is called decoder. Okay, and the way we designed it, as I told you last time, is for each output I need only one AND gate. Okay, so this is D0, D1, all the way until D3. Okay, and then when the input 0, 0, I want the output. I want the output here to become 1. That's why I'm gonna put here A prime, B prime, which is the min term. This is the min term. Okay, A prime, B prime. Same thing, for example, here for number 3, it has to be AB. Okay, and so on. That's very simple. Is that okay? So this is decoder. The second one I explained, which has different functionality, but the structure or the logic circuit is very close. Okay, the second one is called multiplexer. So in case of multiplexer, okay, here always you have one output. You don't need to think about it. Always one output. Is that okay? And if you have here in the input, if you have 2 to the power in inputs, so we have something here, we call it selectors. Any selectors. So this is selector. Okay. And again, we have here, this is input 0, input 1, all that, for example, until input 3, for example. So in this case, we have 4 inputs. Because it's 4 input, I should have 2 selectors here. I'm going to call them AB again. Okay. And what this one is doing is, if the input is 0, 0, so it's going to connect input 0 to here, to the output here. What do you mean by connect? I mean it's equal. So if this input is 0, this one is 0. This one is 1. That's it, equal. Okay. It's not physical connection, but it's equal. The value is equal. Okay. Same thing here. If you have here number 3, which is 1, 1, so actually Y is equal to whatever 0. Is that okay? And now look at the logic circuit. So functionality looks somehow different because this one is not a switch. You don't connect, it's not a switch. You just, what you show here, what you show here is actually the value of the input, the binary value of the input here, okay, in decimal. Okay, what is this value? 1, and other ones are zeros. But here, it's like a switch. You connect the output to one of the inputs here, okay? And that's why I'm telling you, it's very close to this one. So the way you are going to design it is still for each input, I'm going to use one AND. Okay, so this is similar to this one. However, because we have only one output, or all these ANDs are connected together using OR, and this is the output. This is one difference. Okay, so similar to this one, for each case, we have one AND, but all of them, everything all together to get one output. This is okay. The second difference is I'm going to use the same thing like this one, exactly the same thing. But for example, here I'm going to put A prime, B prime. But I'm going to input here I0. Why? Because A prime, B prime is going to give me 1 here. But if A prime, B prime, 1, 1, and we have I0, so I'm going to get I0 here, whatever the value of I0, okay? So it's almost the same idea. Here, only one AND is so here, always what you see here, if the value is 0, 0, so this one is going to produce 1. All the other ones are off, produce zeros, okay? Because the way it is designed, if the input 0, 0, the two inputs here are 1, 1. But for all the other ones, at least there is 1, 0. So they are going to be zeros, okay? So I can say only one of them is going to be active. It's the same thing here. So what happens here, if the input is 0, 0, so this one is producing 0, 0, 0, 0, 0. So I can say they are not active. Because using A prime, B prime, I selected this one. So that's why it's called selection, okay? And then I'm going to get here I0, whatever the value of I0, if it is 0. And as you know, if you have OR, and this OR has a lot of zeros, and then it has X, the output is X. That's it. You got what I'm saying? And this is the case here. If the input is 0, 0, all of these are going to produce 0, 0, 0, 0, 0, because this is similar to the decoder, okay? But here, because this 1, 1, and you know from AND, 1, 1, X should give you X. You know from OR, 0, 0, 0, X is going to give you X. You got what I'm saying? Any questions? Okay, and then also, last time, so this is one way to design the multiplexer. You can design it using AND gate, as I did here. And this one very close to the decoder. Is that okay? Today, I'm going to explain another way to design the multiplexer using a buffer, 3-state buffer, okay? So last time, I explained what I mean by buffer. So buffer, it's like a triangle this way. There is no bubble, so it's going to be triangle this way. From the logic point of view, it doesn't do anything. From the logic point of view, if the input X is going to give you X. It doesn't do anything for logic, okay? But for electronics, it's very important, as I told you last time, okay? Because actually what this one is doing is going to take very little current, and then it's going to provide too much current here. But how is this going to help me in design, in logic? I'm going to tell you, as I explained last time. If you have AND gate, okay, and then I told you the fan out is 3. What it means? It means this one you cannot connect more than 3. Why? Because the current coming from here is not enough to drive, to give enough current for more than 3. You got what I'm saying? So in this case, to solve this, what if I want to connect more than 3? Okay, in this case, you can put here a buffer. So you can make it this way. I can make this one, and then I put a buffer here. In this case, I can put more, okay? So that's what we call a buffer, okay? And in electronics, you will learn how you can design it using transistors, okay? The other thing is, we have also what we call 3-state buffer, okay? Or tri-state buffer. Sometimes we use different names. So the idea here is going to be exactly the same thing here, but I'm going to add a control here. So it's gonna be like a triangle. It has input and it has output this way. And then I'm going to add a control here, okay? For example, I'm going to call it A, for example, okay? So the idea here is, if A equal to 0, so actually this one becomes like open circuit. We call it high impedance. High impedance means open circuit. It's not connected, open circuit. Is that okay? So when it is 0, so the electronics here is going to make it open circuit. We call it high impedance. It's not connected. Okay. The other thing here, if A is equal to 1, it becomes like a short circuit. Very simple. Is that okay? And then that's what we call three-state buffer. And then we have some variation of this one. We have some variations of this one. Sometimes it's the same thing. This one also has, when it is short circuit, also it has a buffer inside it. You got what I'm saying? So it also has a buffer. I don't need to say, but this one also has a buffer. Okay. When it is short circuit, it can provide too much current. Anyway, so we have variation of this idea. So for example, one of the variation, I can put a bubble here. And that's what we're going to do all the time. I told you before, guys, when you see a bubble like this one, it's not different from what I said before. When you see without a buffer, this one we call it active high. That means if you want to enable, you have to put 1 because it's active high. When you see a bubble this way, it means active low. Okay, so it means if C is equal to 0, it becomes a short circuit. So the opposite of this one. If C is equal to 1, it becomes open circuit. Because you can see this one. You can see this one actually similar to this one, but you just added an inverter here. You got what I'm saying? So you can see this one is similar to this one, but you just added inverter here. So that's why if I put here 0, the inverter is going to make it 1 to turn it on. Is that okay? Any questions? We have also, okay, I'm going to show you. We have also some other variation. Yeah. So this is the basic one I explained. This is the first variation I explained. We have other variation. For example, I can put a bubble here and I can put a bubble here. So what this one is doing, I told you, if you put here 1, you make a short circuit. That means C should equal to A, right? But here, if you put this one here, that means C should equal to A prime. You invert the input. So the output doesn't equal the input, but you invert the input. But it's still a buffer. It's still doing a buffer. Okay? Anyway, so same thing here when you see a buffer here. So it's going to invert the input. Okay? Anyway, just a variation from the three. Sometimes they call it tri-state buffer or three-state buffer. Any questions? Okay, now I'm going to explain how I can use, I already explained how I can use AND gates to design multiplexer. I have explained it. Now I'm going to explain how can use the three-state buffers, okay, to design a multiplexer, okay? Remember, very easy. This is just a switch, just like a switch, okay? If I put here 1, you connect. 0, disconnect. Very simple, okay? So let's see if I want to do 2-to-1 multiplexer. Look how I'm going to do it. Look here. So in this case, the number. So here I have the number of three-state buffers I need is equal to the number of inputs. So if you have 2 inputs, so I'm going to need two three-state buffers. As you see here. So look at the idea. Very simple idea. So what happens here is, in case of 2-to-1 multiplexer, so in this case, I have only one select, one input or 1 bit for select here, okay? So either I'm going to select, so this is input 0, this is input 1. That's it, very simple one, okay? So what happens here, when the input is 0, okay, without looking at the details, Y has to equal to A. Is that right? Because this is 0. When the input is 0, this is how multiplexer should work. Y should equal A. A is actually input number 0. If the select is 1, so Y has to equal to B, right? Which is the input 1. It has to work this way. Let's see if it is working this way or not. Look here. The idea is that here, when I put 0 here, this one becomes 0. And because the control is 0, this one is open circuit. You can see it like open circuit. Okay. But because the inverter I put here, this one becomes 1, and this one becomes a short circuit. So actually, so what I did here, this is A, and this is the output here, Y, and then I have open circuit here. That's exactly what I did. So Y should equal to A. Is that okay? When the input is 0. When the input is 1, when the input is 1 here, look what's going to happen. I'm going to, this one short circuit, but this one is going, this one, because this is in, this one is becomes 0 because of this inverter. So this one is going to open. Okay. Let's make it simple. Number one, if you want to use a 3-state buffer to create a multiplexer, number one, the number of buffers you are going to use is equal to the number of inputs you have. This number one. Number two, always only one of them is connected. Other ones are disconnected. Always it has to be this way. Okay. So in this very simple example, based on the input, when it is 0, this one connected, and then this one is connected, and the other one has to be disconnected. Now, let's see, what if I want to make like 2 to 4? Any question here? Okay. What if I want to make 4 to 1? Sorry, 4 to 1 multiplexer. So here we have 4 inputs. Okay. We have 2 selectors here, and then we have 1 output here. Is that okay? 4 to 1. So as I told you, for 4 to 1, as you see here, we have here four 3-state buffer. The first one is connected to number 0, number 1, number 2, number 3. And all outputs are connected together to the output. Okay. And as you will see right now, based on the selection you have, only one of them is connected and the other one should be disconnected. It's not allowed, or it doesn't make sense to make more than 2 connected, right? Only one is connected. So how I can do that? Okay, only one is connected, others are not connected. I'm gonna use decoder for that. So this is, I want to make it easy, guys. Listen to me. So this is not a decoder. I'm using a decoder. This is a multiplexer, but I'm using a decoder to make multiplexer. So actually, this is like a black box this way. Okay, forget whatever's there. It's a multiplexer. But inside this multiplexer, I used a decoder. Okay. Anyway, so let's see how it works and why you use the decoder. I'm going to tell you why. Okay, because decoder, only one output is 1. All the other ones are zeros, and that's what I need here. I need only to connect one of them. Okay, by outputting 1. Okay. Anyway, so let's see how it works. So the idea here, I'm gonna control which one is connected and which one is disconnected using the output of the decoder here. Look how it works. This is the selection I have. So if I select 0, 0, if this is a corrected decoder, so actually the output has to be I0. Yes. Okay. How it works? Very simple. This is a decoder when the input 0, 0. So I'm gonna get here 1, and then I'm gonna get 0 everywhere. And because this is 0, this is open circuit, open circuit, open circuit, short circuit. Very simple. So I'm gonna get I0. Okay. Look for something else. For example, if I put here number 3, 1, 1, what's gonna happen? So 1, 1. So number 3 is 1. All the other ones are zeros. By this way, this one is connected and the other ones are disconnected. And in this case, what I'm gonna get here is actually I3. Very simple. You got it? So based on the selection I have here, only one output is 1, everyone else is 0. When the output is 1, so I'm gonna connect one of them so that the output is equal to I0 or I1 or I2 and so on. Okay. Also, I explained the idea of enable here. So this enable for the decoder, if the decoder is gonna work or not. I told you before, and in this case, this is also enabled for the whole multiplexer as well. So for example, here, if the input is 0, so this decoder is not working. So all outputs are 0, 0, 0, 0. Okay. So all of them are open circuit. Yeah, because the multiplexer also is not working. Any questions? Any questions? Okay. So now I'm gonna teach. I am done with multiplexer. So now I'm gonna tell you about something we call demultiplexer. Always you can tell from the English name, multiplexer, demultiplexer. So demultiplexer is gonna do the opposite of multiplexer. Okay. So what multiplexer is doing before I think about the opposite. So in case of multiplexer, here, it's as I said, or maybe I have a, yeah. So here, this is the symbol we use for multiplexer. So in multiplexer, you have different inputs here. If you have 2 to the power n inputs, okay? So here you should have n selector. And then based on the input here, we have only one output. In multiplexer, we have only one output. And then it's like a switch. Yeah, that's why you see this is very interesting figure here to understand. It's like a switch. Either the output is connected to input 1, input 2, input 3, or input 4. How I can control which, it's a switch, connected to which one? Using the selector here. Okay? So by using the selector, I can select the output is connected to 1, 2, or 3. Okay, based on that, what is demultiplexer? Demultiplexer should do the opposite. So as you see here in demultiplexer, this is the symbol usually we use it this way. Okay, so we have here only one input instead of one output. So now we have only, so it's going to be like the opposite, the other way. Okay, so I have here only one input. Okay, and now I have 2 to the power n outputs, and then here we have n here. Okay, and all what I'm going to do here, I'm going to just to connect, I'm going to connect this input either to 1 or 2 or 3 or 4. Okay, it's going to be like a switch this way. It's going to be the opposite. So if this one is going to select one of this input to present it here, this one is going to do the opposite. So it's going to take whatever there, it's going to distribute it here. Based on the selector. Okay. So that's what we call a demultiplexer. By the way, multiplexer and demultiplexer is widely used in several things. For example, like in communication. In communication, usually what happens is that, for example, if I want this guy, I want this guy to communicate with this guy, for example. So what I can do is I can select using multiplexer this way, and then when you come here, I can select this one to come to here, for example. You got what I'm saying? Or if I want, for example, this guy to communicate with this guy, so I can make the connection this way, so that whatever data you hear is going to go this way. Okay, so usually we use it this way. Any questions? Very important to understand this, like a switch here. You select someone, you have several inputs, so again, you should understand, if you are making your capstone design, you should understand if this problem you want to do something, you should understand if this can be done using multiplexer, decoder, or whatever. Okay, so here in multiplexer, if you want to select, you have several options here, and I want to take the data from one option. Okay, and then here you can do the opposite. So if your problem or if your design needs something like that, you need multiplexer and demultiplexer. So now let's talk about demultiplexer. How can we design demultiplexer? Okay, so here what I'm telling you here, a demultiplexer is not a new device. I can use the decoder with an enable. Please add this enable here. Okay, I can use a decoder with an enable. This can act as a demultiplexer. How? That's what I'm going to explain how. So a decoder with an enable, it can act as a multiplexer. So I don't need to make a new design. Okay, how? I'm going to tell you how. Again, so here the input of the decoder becomes the selectors in the multiplexer. So the inputs of the decoder are going to become the selector. Okay, the enable here is not going to act as enable in the multiplexer. It's going to act like input. So I'm going to use the enable of the decoder to become the input. Okay, so here, I have input. So this is the input is here. I have selectors. These are the selectors here. and I have outputs. These are the outputs here. Okay. So if I do this way, you will see this decoder is exactly doing the same thing like a multiplexer. Let's see the example here. This is the same truth table I explained before for a decoder with an enable. Look how it works. The first case here, when the enable is 0, that means I need to output 0, right? And this is exactly what happens in this decoder. So if the input is 0, so regardless what you have here, you are going to get zeros. Okay. But if the input is 1, so based on your selection here, based on what you are going to select, this one you can choose, or this one can present on D0 or D1 or D2 or T3. Is that okay? So this is exactly what when I do in multiplexer. In case of a multiplexer, okay, when I select when the input here is 1, okay, and I wanna, for example, I'm gonna use D2 here, so I wanna see 1 here, okay. When the input here is 0, okay, so actually I wanna see 0 here, and so on. So you can see the functionality here is same thing like a multiplexer. If you wanna connect, if you have here a device, okay, and this device you wanna give this device 0, so all what you have to do, have to put 0 here in the enable. If you wanna give this device 1, okay, so all what this is the input. If I put here 1, you are gonna get 1 here. For sure, you need to select this device. You got what I'm saying? So the functionality here is very close to or similar to the demultiplexer. So I'm gonna just twist the decoder. Instead of the selectors here, instead of the inputs in the decoder, becomes the selectors in the multiplexer. The enable becomes input, and the output here is similar to the output. So I don't need a new design. Any questions? Okay, so I'm gonna go back to the where I left here in the decoder. Yeah, so I already explained this decoder. I told you we have active low outputs and active low enable, as you know. Okay, as I already explained this one here. This one is 3 to 8 decoder. So if you have here the input are 3 and you have 8 in the output, and this is the truth table of this one. Very simple. If the input number here is 0, so D0 is 1 and everyone else is 0. Okay. If the number here is number 6, for example, D6 is 1 and everyone else is 0. That's it. Very simple. And it's the same thing for every here. How many entries we have? We have 8 entries. So if you want to design this one, we need 8 AND gates. 8 AND gates, okay? So yes, so we need 8 AND gates. But how many inputs you have here in the AND gates would be similar to this one, okay? For example, in case of D0, I'm gonna make it X prime, Y prime, Z prime. That's it. Yeah, that's what I explained also last time here. So I need 8 because I have 8 cases, okay? And then here, X prime, Y prime, and so on. And based on the input you have, only one of them is going to output 1 and everyone else is going to output 0, based on what is the input, okay? Because these are min terms. Any questions? Okay, good. So what I'm explaining here is just I'm going to show you if I want to make 3 to 8 decoder similar to this one, 3 to 8, similar to this one, similar to this one. But I want to make these 3 to 8 decoders using 2 to 4 decoders. I'm going to show you how I can make it, okay? So I want to make same thing like this one here. Yeah, so I want to make same thing like this one here, but I'm going to use inside this one, I'm going to use 2 to 4 decoder. I'm going to explain how you can do it, okay? So this is 2 to 4 decoder with an enable. This is 2 to 4 decoder with an enable. Is that okay? So and this is the truth table is here. This is what I should. So I'm gonna show you how I can combine these two to how I can connect these two together so that I'm gonna get 3 to 8 decoder. Okay, look at the idea. Look how it works. Very simple idea. Look here. This is the input, right? This is similar to what I explained. When this one is number 0, so D0 has to be 1, everyone else is 0. When this one is number 1, 2, 4, so 5, so D5 has to be 1, everyone else should be 0. Is that okay? So what I'm gonna do is, I'm gonna take the last column here, I'm gonna take this one here, and then I'm gonna connect it here, okay? And then I'm gonna use inverter here as you see, and then will be the enable here and the enable here. So I'm gonna use one variable for enable, okay? But I have to make sure to put inverter here. So what this inverter is gonna do? Using this inverter, I can make sure only one of them enabled at any time. It's impossible to enable both of them because of the inverter, right? So if I put here 1, this one is enabled, but this one is disabled because of the inverter. If you put here 0, so here you put 0 and here you put 1. So actually, what I'm putting here and here is a complement to each other. So that's why I'm putting this inverter to make sure only one of them is enabled. And then after that, X and Y, I'm going to input X, Y to both of them. So again, make it very simple. What I'm saying is, here, X and Y are going to be input here, also input here. Okay. And then I'm going to use E for enable and disable of both of them. Look at the idea. Look how it works. If I cut here, look here, very important. Look here. So if you look at 0, 0, 0, 0, and then here we have 1, 1, 1, 1, 1. What it means? It means because this one is 0, 0, 0, this guy is enabled. And because this one is 1, 1, 1, this guy is enabled. You got what I'm saying? So in this half, this one is enabled. In this half, this one is enabled. Is that okay? And then now I have 2 variables. You remember, when you have 2 variables, you have 4 cases, 2 to the power of 2, 4 cases. And these are the 4 cases are here. So here, this one is already disabled. Forget it, disabled. So here, based on the enable, so now I can select starting from D0 until D3. Why? Because if it is 0, 0, so I'm going to select the first output here, because this is the one that's enabled. Okay, and the input here is 2. Okay, so I can select one out of 4 here. Okay, but remember, for all these 4, this bit is 0. This bit is 0. So if I select 0, 0, this number becomes number 0. So that's why here D0. So I'm gonna get D0 from here. The first one here has to be D0. Why? Because this one will become 1 when it's 0, 0, 0. It's number 0, right? And now, in case of number 1, which is D1 here, D1 here, actually, when the total input, which is 0, 0, 1, is actually number 1, right? So it makes sense. So all what I'm gonna do is D0 is gonna be D0 for the 3 to 8 decoder, D1. So I'm going to take D0 to D3 from here, but here I'm going to take 4 to 7. Man, wait a second. Can make it easier? I'm going to make it easier, but listen to me. Look here. I'm going to show you the trick here. The trick is, if you look at these 2 bits here, this one actually, look here, and look at these ones. They're the same, right? 0, 0, 1, 2, 3. It's the same, right? But when I put here 0 at the end, so it's gonna get 0, 1, 2, 3. But when I put here 1 at the end, I'm gonna get 4, 5, 6, 7. You got what I'm saying? That is why listen to me, when the input here is 0, 0, and this one is enabled, so here E is 0, okay? So here I'm gonna get T0 from here because this number 0. But if this one is 1, so I'm gonna get actually D4 from here. D4. Why? Because this is number 4, 1, 0, 0 for the same input here. Okay. So you can see here something very interesting. If this is like, if you think about X and Y as a truth table, it just repeated here, going to be repeated. Only the last bit is different. Okay. So if you think about it a little bit, you will see if I do the design this way, and when the input is 0, okay, always XY, regardless which decoder is enabled, always XY has the value 0, 0, or 1, or 2, or 3, always, okay? But the difference is that when the first one is enabled, okay, so it's going to be 0 and D0, 0, which is close. So I have to take the first one here, I'm going to call it D0, and so on. And the one 0 should be D4 to D7. Any question? The trick is clear. So what I did, it's like I cut the big problem to small problem, okay? This is the whole space. And because of using 2 decoder, now I'm gonna work on this one and then I work on this one. Any questions? Okay. I can do the same thing, exactly same thing. But here, I'm gonna use 2, 3 to 8 to create 4 to 16. It's the same thing, as you will see right now. You got what I'm saying? I just make it bigger, but it's the same thing, as you will see, okay? So if you wanna do that, it's the same idea. Let me go to the, yeah. No, I don't have a truth table for this one. Yeah, I can show on this truth table, okay? Or yeah, so for example, here it's the same thing. So what I'm gonna do here is W, we have W, we have X, we have Y, and we have Z. Is that okay? And then we have here 8 zeros, because this is 1, 2, 3, 4, 1, 2, 3, 4. We have 8 zeros, and then we have 8 ones. 1, 2, 3, 4, 1, 2, 3, 4, 8 ones. Is that okay? Similar to what we have here. So here we have this one. I just cut it into half, and this becomes like a truth table for two input and 2 input. It's exactly the same thing. But here, so here, if you look at the numbers here, it should be 0, 1, 2, all the way until 1, 1, 1. So this part will be the same here, 0, 0, 0, 1, 2, all the way until 1, 1, 1. So it's the same observation. Just, yeah, this part here, when W is 0, 0, 0, actually, I'm going to have 8 cases here for 3 variables, X, Y, Z, okay? And these ones are similar to this one. So similar to what I did before, I'm going to input X, Y, Z to both of them, input to both of them, okay? To select one of out, to select 1 out of 8 output. So this one has 8 output and this one has 8 output. And based on W here, when W is 0, 0, 0, so actually the first one is enabled. When it is 1, 1, 1, the second one will be enabled. Okay, so that's why when the first one is enabled, I'm gonna get numbers from 0 to 7, and you can tell from here. Look at the numbers here, 0 to 7. But when the second one is enabled, I'm gonna get numbers from 8 to 15. Any questions? Okay, how I can tell if this is correct or not? Very simple. You know how 4 to 16 decoder should work. You know, right? 4 to 16 decoder, we have 4 inputs, 1, 2, 3, 4, and we have 16 outputs. When the input is 0, 0, 0, so the input number 0 has to be 1, and everyone else should be 0. That's how it should work. Try to see if this circuit is doing the same thing or not. If this circuit is doing the same thing, like what I'm expecting from 4 to 16 decoder, so it should be okay. Okay, so I designed it in such a way, so that when the input is 0, 0, 0, 0, okay, so here the first one here becomes 1, and the first one here, I'm gonna call it D0. When the input is number 5, okay, so here number 5 becomes 1. That's why I'm gonna call it D5, and so on. Okay. So anyway, there is no big difference between the same idea. This one is exactly similar to what I did here, but I just make it bigger. Any questions? Okay. I can make a decoder. Okay. Usually for a decoder, usually if you have here, usually it's n to 2 to the power of n. Usually, for example, if you have 2 to 4, for example, if you have 3 to 8, okay, and so on, 4 to 16, usually. However, in some cases, like this case here I'm explaining, I just want to tell you about this case. That's it. In this case, I may need a decoder that is 4 to 10, not 4 to 16. You understand what I'm saying? Okay. So that means, so usually it has to be 16. But I'm not gonna use all the numbers here until 16. I'm gonna only use until 10. Okay. So that's why. So if you see here the truth table, you have here number 0, 1, 2. So until here, number 10. So what about the next number? Because this is 4 bits. 4 bits can take numbers up to 15. So these numbers are not going to be used. Why? Because here I'm assuming the input is BCD. So this decoder is exactly similar to 4 to 16, exactly similar to 4 to 16. However, I'm going to cut. I'm going to cut here. I'm not going to continue. I'm going to cut here, right? So in this case, that's what I need, right? So for example, I have 4 input. I have 10 outputs this way, okay, instead of 16. Okay, and the input here has to be between 0 to 9. So I should have 10 inputs, not 16. You should not input anything greater than 9. I think this is 9. Yeah, you start from 0 all the way until 9. So you can see if you have a decoder like this one, so you can see it like you convert BCD to decimal output. So the input here is BCD, binary number from 0 to 9, and the output here should be, you select a number from 0 to 9. Okay, so it becomes like a converter from BCD to decimal output. Any questions? Yeah. How can you design this one? Similar to what, nothing is new, similar to what I explained to before. Okay, so here because the output here, the only difference, as I also explained before, because the output here is inverted. So instead of using AND, you are going to use NAND. That's it. This is the only difference. But everything else is the same. For example, here you have 0, 0, 0. So I'm going to input here A prime, B prime, C prime, D prime. Okay. That's it. So here it's the same thing. So nothing is new. Exactly same. I just want to, again, here nothing is new. The only thing I want to tell you, sometimes it doesn't need to be 4 to 16. That's what I just want to tell you here. Sometimes I need 4 to 10, for example. Okay, so that's why, to be more accurate, although listen to me, although most of the time, actually, to be honest with you, most of the time, it's actually, if the input is in, the output has to be 2 to the power n for decoder. This is the usual case, or this is usually what we do it. However, in some, to be more accurate, I have to say, if the input is in, the output has to be less than or equal to the power n, to be more accurate. But most of the cases, it is 2 to the power n. But it can be less than or equal to the power n, like this case. Okay, to be more accurate. Yes. Any questions? Okay. So here, I just want to tell you, we have this chip 139. Inside this chip, there are 2 separate decoders in one chip. Okay. So if you see here, we have here, this is, as you see here, it's active flow outputs. So this is one decoder. So this is one decoder. This is a second decoder. They are completely separate. It's like when you have a chip, this chip has two AND gates. They are separate. Same thing. So this chip has 2 decoders, separate decoders. Okay. So that's why the first decoder has 4 outputs. The second decoder has its own 4 outputs. Is that okay? Also, the first decoder has two selector here. The second one has two selectors. They are separate. I'm repeating the word separate. So don't think there is any connection between. They are separate. Okay. Also, the first decoder has one enable here, and the second decoder has one enable here. And this enable is active low. That's easy. Every time you see this bubble, that means it's active low. So in order to enable, you have to put 0, right? So the two decoders are separate. Any question? In the coming lab, you are going to use 138. This one 139. Okay, you are not going to use this one in lab. I just wanna tell you these decoders can. I'll just give you one example for a real chip that has two decoders. Okay, but in the coming lab, we are going to use 138. I explained in the video of this lab, or that's what you are going to use in the coming lab. So this one actually it is 3 to 8. So these are the 3 input. This is the selection 3 inputs. And this is the outputs are here. 8 outputs are here. Okay. And as you see, the outputs are active low. Active low. The outputs are active low. Okay. And this chip actually it has three inputs for enable. Sometimes we do that. Listen to me. Sometimes the device has only 1 bit or 1 input to enable or disable. Sometimes we have more than 1. Just to give you more flexibility when you design. Okay. So for example, this chip or this decoder, it has three enable. Is that okay? Now the question is that how can I enable it? So you are telling us we have 3. One of them is active high, so it has to be 1. 2 of them should be active low, 0 and 0. The question is that, so I have 3. Is that enough to enable one of them, to enable the whole chip? The answer is no. In order to enable the whole chip, you have to make sure the 3 inputs are enabled. If only one of them is disabled, the whole chip is disabled. Very simple. Okay. So what I'm saying here, again, this is always the case. You are going to see in logic, in even not only in decoders. So in the future, when you get a logic chip, sometimes they do the enable this way. So here, in order to enable this chip, I have to put here 1. I have to put here 0. I have to put 0. Is that okay? By this way, this chip is enabled. I have to enable the first one, and I have to enable the two as well. Any other thing, it is disabled. Don't think about it. Okay? That's why here this is reflected in the truth table here. So in the truth table here, this part is enabled. That's why you can see here 100. So here when I put 100, the chip is enabled. Anything else, so if I put here 0, so if I enable this one, sorry, if I disable the first one, and then you put whatever, anything you put it here, it's not going to make a difference. It is just disabled. So very simple. So you have to make sure the 3 inputs should be enabled. Okay. So that's why here in this case here, let me cut it here. Okay. So here it is disabled. And when it is disabled, all outputs are 1s. Because it's active low. In case of active low, when it is disabled, all the outputs are 1s. In case of active high, if the outputs are active high, when it is disabled, all outputs are 0s. Everything is inverted because instead of using AND, I'm going to use NAND. Everything is inverted. Okay. Any questions? And now here it is enabled because now it is enabled. If the input is number 0, okay, so the output 0 is 0 and everyone else is 1s. If the input here is number 5, okay, so the output number 5 is 0, everything else is 1s, and so on. Any questions? This is the shape you are going to use in the coming lab. Okay. Okay. So now I want to show you also something interesting. I want to use 2 of 138, this chip. I want to use 2 of this chip, which is 3 to 8, to make 4 to 16. 4 to 16, okay? So this idea will be similar. Yeah, so here it will be similar to this one. So this idea will be similar to this one. I'm going to use 2 from 3 to 8 to create 4 to 16. It will be very close to this one, okay? But there is a small difference. What is the small difference? The small difference is here we have only one enable. In the other one, I have 3 enables. So how I'm going to use them? This is the only difference. Okay. So I'm going to show you how. Yeah. Look how I made it. Okay. So similar to what I did here, I want to compare to this one, just to make it easy. So what I did here, I have 3 enables. Okay. So still I'm going to use one enable like this one here and put inverter here. Okay. So I'm going to use one enable this way, one of them. Is that okay? And that's what I did. So if you look here, the selector here, okay, they are going to have W, X, Y. Is that okay? And then I'm going to use Z, which is the last input here in the Z. In Z here, I'm going to connect, as you see here, to this one here. Also, is going to be connected to. So I'm gonna connect. Yeah, this is Z. I'm gonna connect it to this one here, and then I'm gonna connect it to this one here. But wait a second, it doesn't have an inverter. You don't need inverter because the way I did it is when this one is 0, okay, so this one is enabled, but this one is disabled. You don't need inverter here. If the input is 1, so this one is enabled, the other one is disabled. So in the previous one, I used the inverter to make sure only one of them is enabled at a time. But it's already, it can be achieved here if I just, so this is going to become, this one becomes an input. So here you have W. I'm sorry, you can hear, for example, you have W, X, Y, Z. Okay, so I can put here W and here X, Y, Z. X, Y, Z are connected here and here at the same time for the selector. So this is exactly the same thing I did before. But here, what I'm going to do for W here, W, I'm gonna get G1 here, I'm going to get this one. So that when W is 0, so this one is enabled, but this one is disabled. And when W is 1, okay, so this one is enabled, but this one is disabled. Exactly same thing as I did before. Is that okay? Now, I still have two other enables. What you are going to do about them? Okay. What I'm going to do is, one of them, I don't need to do anything. That's why I'm going to enable it all the time. So this one, I'm going to connect to booster 5. So I'm to enable this one all the time. This one here, I'm going to make it 0 to enable it all the time. So I have 3 inputs. One of them, I don't need it. So I'm going to make it enable all the time, here and here. The second one, I used it to connect to one input. The last one, I'm going to use it to make enable for the multiplexer, for the 4 to 16 multiplexer. So what I did here, the last one here, which is, yeah. So here, I'm going to take this one here, as you see, okay, with this one. This will be the enable for the whole multiplexer, okay? Let's see how it works. If this one is 1, okay, so actually this one here, you put 1 here and you put 1 here. That means this one is disabled and this one is disabled. So the whole multiplexer, the 4 to 16 multiplexer is disabled. If you put here 1, okay? If you put 0, here, both of them are going to be at least enabled in this bit. Because as I told you, you have to enable the 3 bits, okay? This bit is okay. Any questions? So again, if you want to understand this slide, I'm not going to make it easy. First, you need to understand this one first, okay? Because this one is similar to this one, but the only difference is that here we have only 1 enable, but in the other one, for every decoder, we have 3 enables, 3 of them. So what I did, I took 1 enable to do something exactly like this one, 1 enable. Another enable, I don't need it. So I'm going to make it enable all the time. Another input, right? That's number 2. The third one, I'm going to connect them together, and then I'm going to make this is the enable for the whole multiplexer, for the 4 to 16, sorry, for the whole decoder, 4 to 16 decoder. Any questions? Anyway, it's fun just to connect this way and see how I can make sure this is the connection is correct or false. Very easy. You have a truth table. You have a truth table for 4 to 16. Put the input here and see if this one is doing what I'm expecting or what should 4 to 16 decoder do. Okay. If it's doing the same thing, it's correct. Okay. Any questions? Let's have more fun. Okay. So let's for example see this one. I want to create 4 to 16 decoder, 4 to 16 decoder using 2 to 4. 2 to 4 decoders. Oh man, make it difficult. No, it's not, but I'm going to tell you how it works. Look how it works, okay? So what the way it's going to work is, as you see here, in case of 4 to 16, how many outputs do you need? I need 16, right? So this decoder can give you only 4. So I'm going to use 4 of them. This gives you 4, 4, 4, 4. This gives you from D0 until D3, D4 to D7, D8 to 11. So everyone gives you, is going to contribute by 4. So total now we have 16. Is that okay? Is that okay? And now X and Y is going to be connected to all of them here. The selection here. Is that okay? X and Y. Okay. Okay. This number 1. Number 2. I'm going to use the enable here, and the enable here, and the enable here, and the enable here, right? So that only one of them should be enabled. The other one should be disabled. But can you make it easier? Yes. The truth, look at the truth table. The truth table is going to tell you how can you make it. It's going to make it easier. If you look at the truth table here, look here, guys. Here, if you look at this part here, so again, let make it simple. Okay, number 1, I'm using 2 to 4. That's number 1. So I have here 2 inputs here. So I'm going to use the first 2 inputs here for all of them. Easy. Everyone give you 4. So actually I need, in total, I need 16. So I need 4 of them for decoders. That's not, okay. One more thing here. Look here. Now, here, in case of 0, 0, 0, 0, I have to find the way in order to enable this guy in these 4 cases. And then, once I enable this guy, if it is 0, 0, I'm going to get D0. And D0 is equivalent to 0, 0, 0, 0. Correct. If it is 0, 1, okay, so I'm going to, D1 is 1, and this is number 1. D2, D3. Same thing here. I have to find a way when the input is 1 in these 4 cases, I have to enable this one and disable everyone else. And now, if you enable this one here, now, and then using the same selectors 0, 0, or 1, 0, or 0, 1, or 1, 1, what this number is when it is 0, 1, and then 0, 0. What this number is? This is number 4. Okay. What this number is when it is 0, 1, and then 1, 1. What this number is? It's 7. So this one should give you the number from 4 to 7. Okay. That is why what I'm doing here, same thing here for 1, 1, 0 here, this one should be enabled. And based on the binary numbers here, this one has to give you the number from 8 to 11. Because this is 8, 9, 10, and so on. Same thing here. This one should enable this one. Is that okay? Based on these values. So how I can do that? How I can, based using this value, this one is enabled. 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 How I can do that? I'm going to use another decoder, as you see here. So in the other decoder here, okay. In the other decoder, as you see here, this one here, if I put 0, 0, so actually this one is 1 and then 0, 0, 0, and this will enable the first one. Yeah, that's what I want to do, right? Yeah. So now what if this one is actually number 1? Number 1 means 0, 1. So actually, this one here is 1. This is the enable, guys, okay? This is the enables. 0, 0, 0. So in this case, I'm enabling the second one, and so on. So let me see it in a different way. Look here. We have 4 variables. I'm going to use 2 variables to select 1 decoder out of 4. And then I'm going to use the other 2 variables to select 1 output, or to output output 1 on 1 output out of 4. You got it? So I'm going to select these 2 here. So these 2 are going to be for selection. Okay. So this one should only enable 1 of them based on these 2 values. Okay. And by the way, this one has an enable. This will be the enable of the whole decoder, the 4 to 16 decoder, this enable. You know why? Because if this one is disabled, the 4 are disabled. So everything is disabled. You got what I'm saying? So here I'm going to use this enable here. This will be the enable for the 4 to 16. If I put here 0, so here the output is 0, 0, 0. So all of them are off. So nothing is working. Any questions? Good. So now I want to also to tell you about another different type of decoder. So what I have explained so far, if you have n to the power of n decoders, 2 to 4 decoders, 3 to 8 decoders, and so on. Okay. We have something different also, different types of decoders, like for example, BCD to 7-segment decoder. Okay, so this one is not like n to 2. Sorry, this one is not n to the n decoder. No, that's a different type of decoder. We call it BCD to 7-segment decoder. Okay. By the way, this one we have already used it in one lab. There was a chip. I told you this chip, if you remember. Yeah, so this is exactly what I did in one lab. But today, I'm going to show you how can we design it. So in one lab, we used a chip, and this chip was called BC2 to 7-segment decoder. If you remember, you need to connect it to the 7-segment, right? And if you put 0, 0, 0, you are going to see number 0 here. If you put number 1, you will see number 1, and so on. Is that okay? That's already already used in one lab. So this BCD to 7-segment decoder, you have already used it. Okay, how it works, that's what I'm going to say. But today I'm going to give you more details. Okay, what logic circuit I have to put inside here to do this functionality. But let me think first. What this decoder has to do? Okay, I'm going to tell you what this decoder has to do. Okay, so as I explained before in one lab, in 7-segment, I know you will know the details later when you have electronics. So I don't want you to worry now. Just for now, you need to know the minimum information. But when you go for electronics, you will know the details. Okay. So as I told you, we have something we call it LED. So I'm gonna LED. So LED is actually here. Every segment here is LED. You can turn it on or you turn it off. Okay. So every LED has to be this way. That's how this is the symbol. And this is anode. This is what we call cathode. Okay. In order to turn this one on, the voltage of the anode has to be greater than the voltage of the cathode. Okay. Also, you need to connect the resistor. Okay. So this is exactly what we do. So usually what you do is you connect the resistor this way, and then you put here 5 volt and then 0 volt. In this case, the current is going to flow this way, and then you turn it on. Okay. If I put here 0 volt, so actually you turn it off. Okay, because the voltage here has to be greater than the voltage here. So what we did here in the 7-segment, as you know from one lab, every segment alone is like one LED. One LED. That's why you see here we have several LEDs. And by the way, it can be connected in one of 2 ways: common cathode or common anode. So every LED here is actually every LED here is one segment here. Okay. So what I can connect it in one of 2 ways. For example, I can connect all the cathodes together to the ground. And in this case, if I want to turn this one on, So I'm going to put resistor here. I'm going to put 5 volt. So the segment I want to turn on, so I have to put 5 volt at this segment. You put 5 volt. You put 5 volt. Is that okay? There is another way. The other way is, but again, this is, be careful here. When you buy the 7 segment, it will be written on the 7 segment if it is common cathode or common anode. Because what happens, all cathodes are connected together. Okay, here all anodes are connected together. You got what I'm saying? So when you buy, I don't know, I think in the lab this is the one you used, like it was common cathode, I guess. Yes. Do you remember? I think. But there is another type, we call it common anode. So in case of common anode, so here all anodes are connected together, so you need to connect them to 5 volt. And now, if I want to turn this one on, so I'm going to put 0 volt. If I want to turn this one, I'm going to put 0 volt and so on. So we have 2 different types, but I'm going to focus on this one. No difference, exactly same thing. It's just about connection. Should I connect this one is connected to 5 volt and then put zeros if I want to turn anything? In both cases, in order to turn an LED on, the anode has to be greater, the voltage has to be greater than the cathode in all cases. Okay. Anyway, I'm gonna talk about this one here. So now okay, let's return to my point. What this decoder is? This decoder should get a BCD number, and then using this BCD number, okay, so this is a truth table. This is exactly what this decoder has to do. Look here, guys. What this decoder has to do is that this is the input, this is the output. So this decoder is a logic circuit. There is a logic circuit here, and this is the truth table of this logic circuit. Okay, this is the truth table of the logic circuit. Okay, so this one actually has 4 inputs because this is a BCD number. Should be from 0 until 9. Okay, the output here should be 7. A, B, C, D, E, F, because as you see here, this segment is called A, B, F, G, C, D, E. Is that okay? So 7 output. So 4 input, 7 output. The input is a BCD number from 0 to 9. The output here is actually 1 or zeros. Okay? Based on the number I have here, the input, I need to know which segment I have to turn on here in order to see this number. Okay, I'm going to explain it. Look here, guys. So for example, if the input is 0, 0, 0, the output has to be 1, 1, 1, 1, 0. Why? To give you number 0. To see number 0. When you connect the output here to the 7th segment, you are going to see number 0. When the input is number 1, the output has to be 0, 1, 1, 0, 0, 0. Why? Because I want to turn B and C on. That's why it has 1 and 1 here. Turn everything else off. That's why it has zeros. Is that okay? So now I'm going to make the truth table this way. Based on which segment I have to turn on, which segment I have to turn off. Okay. In case of number 9, as an example, number 9, as you see here, all of them should be on except this one has to be off. And that's exactly what I did. All of them should be on except this one should be off. Is that okay? So now you should understand what BCD to 7 segment decoder means. What it means. It means it's going to take a BCD code and then it's going to give you 7 segment code. When you put this code, on the 7th segment, you will see the number corresponding to the BCD code. You understand what I'm saying? So the input is BCD code, the output is 7 segment code. Is that okay? Now, once I create the truth table, all what I'm going to do right now is I want to design, similar to what you did before. I want to design it, okay? So but maybe it's a big design problem, but I just, so here what's going to happen, this is the input and this is output. We have 7 outputs, F1, F2, F3, 7 outputs. So I'm going to take this one alone. I'm going to make K-maps. I'm going to take K-map to simplify it. And then I'm going to have to do it again here, again here, again here. So I have 7 outputs. So I should have 7 K-maps for every one of them. Is that okay? And that's exactly what I did. Yeah. So here, 1 map for A, 1 map for B, 1 map for C, for D, for E, for F. Is that okay? So yeah, again, nothing here is new. This is similar to what I did before. We have 4 inputs and we have 7 outputs. Okay, so this is a function. For each one of them, I'm gonna make a map. Okay, so here for the first one here, this is the first function. Okay, so you can see here we have one here, min term 0, min term 2, as you see here, 0, 2. So I'm gonna see where are the min terms here, and then I created this function. Then I have another function here, another function here. So all of them will have 8 functions here. For these 8 functions, I'm going to use 8 key maps. Okay, sorry, 7. So I'm going to use 7 key maps, and this is the output. This is the result is here. This is the result. So the output A should equal to the input. The uppercase is the input. Okay, this is a BCD, so it has to be A or C or B and G or B prime, C, D prime, and so on. And then after that, yeah, this is what was inside the chip used. Okay, so in one lab you used a chip. Yeah, this is chip here. It has 4 inputs BCD. It has 7 outputs for 7 segment. So it's gonna convert. It's gonna convert the BCD code into 7 segment code, right? So there is a logic circuit there, right? So now I'm explaining, you already used it, okay? But you can design it this way. And this one is called BCD 7 segment decoder. And this type of decoder is different from the one we used before, n into 2 the power of n decoders, okay? But it still is doing conversion. It's gonna convert from one code to another code, okay? So yeah, if you do, nothing is new. Just I get these values here, and then we draw it this way. So this is the circuit that has to be inside the chip you used. The input is actually ABCD, which is the BCD input. The output should be from A until G. Okay, and then you connect. So here you connect the output here to the 7 segments. Okay, any questions? Any questions? Okay. So let me tell you what is left in. So what I'm gonna do, let me tell you what is left here in this chapter. So in this chapter here, yeah, I skipped some parts. So for example, here I didn't explain multiplier yet. That's okay. Comparator, I didn't explain it yet. Okay. I finished this one completely. Okay. Here I finished the decoder, and what is left is encoder. Okay, encoder. That's it. So that's what is left in this chapter. Only these 3 parts. Okay. Next lecture, Wednesday, number 1, we are gonna have a quiz. This quiz is gonna be about, similar to the lab, how can we use decoders to implement the functions, which is similar to the coming lab. So which slide? I just want to tell you which slide you need to. Yeah, I already explained it. Yeah, this one here. So you need to study this one here, this slide, 54, 55, okay, 56. Okay. Also, I explained how can use multiplexer. Okay. Yeah, how can you use multiplexer to implement a function. So you need to study 76, 77, and also 78. Okay. You need to study them anyway, because this will be the coming lab anyway. So the quiz will be about that. Also, what I'm gonna do, I'm gonna put chapter 3 on hold for now. I want to start chapter 4. Okay, next time. That's because, again, I have to start with the parts that I need in the labs first, as long as there is no problem, as long as the flow is okay. You understand what I'm saying? So again, that's okay. So next time, tomorrow I'm gonna post some slides for chapter 5. Okay, I need to start it because that's what we need, not in the coming lab, the lab after, but I need to finish this topic first. Okay, and there is no problem, because what I'm gonna teach in chapter 5 does not depend on the parts I didn't teach here, so it doesn't depend. So it should be okay. Anyway, thanks, guys. We still have 1 minute. I feel guilty.